My name is Muhammad Is. So let's talk about two important concepts in data communication, ARQ and flow control. First, ARQ or automatic repeat request helps ensure reliability data transmission. If any data packets get lost or corrupted during transmission, like over a noisy or unreliable network, ARQ detects that and automatically requests a retransmission. It uses acknowledgements or SEKs to confirm successful delivery and timeouts to detect when a packet needs to be resent. Next, we have flow control. This is all about managing the pace of data between sender and receiver. Without flow control, the sender might send data faster than the receiver can handle, leading to data loss or system crashes. So, flow control helps maintain smooth and efficient communication by making sure the sender doesn't overwhelm the receiver. Together, ARQ and flow control help keep data communication reliable and efficient. Now, let's look at the different types of ARQ protocols. First is stop and wait. This one is very simple. It sends one packet at a time and waits for an acknowledgement before sending the next. It's easy to manage but not very efficient because of high idle time. Next is go back N. This protocol uses a sender window to send multiple packets at once. If an error happens, it goes back and resends everything from the first lost packet. It's more efficient than stop and wait, but it still has some retransmission overhead. Finally, we have selective repeat. Like go back N, it sends multiple packets but it uses both sender and receiver windows. The main difference is it only resends the specific packets that were lost. This makes it the most efficient protocol of the three. So overall, as we move from stop and wait to selective repeat, we get better performance and efficiency. This slide covers the two parts, the responsibilities of ARQ protocols and how our simulation works. First, the key responsibilities of ARQ protocols. Framing. They divide data into smaller frames for easier transmission. Flow control. They manage the pace between sender and receiver, preventing overload. Error control. They detect and fix errors by retransmitting lost or corrupted frames. Now, let's look at how the simulation works. It simulates real network condition by using random packet or SEK losses. It also includes realistic delays based on packet size and bandwidth. The logic of each protocol is applied. Stop and wait sends one packet at a time. Go back N sends multiple packets and goes back if there's an error. Selective repeat resends only the specific packets that were lost. The simulation helps us measure how each protocol performs under different network conditions. This slide gives a quick summary of our ARQ simulation program and why understanding ARQ is important. First, the simulation was developed in the C programming language. It includes three protocols: stop and wait, go back N, and selective repeat, both with configurable window size. We can adjust various network parameters like packet and SEK loss probabilities, bandwidth, latency, timeout, duration, number of packets, and window sizes. It also collects performance metrics such as total packet sends, retransmissions, SEKs, transmission time, and throughput. Now, why does this matter? Reliable communication is essential in computer networks, especially with interference or noise. ARQ protocols form the foundation for many higher level protocols like TCP. By understanding ARQ, we get a better idea of why network performance changes under difficult conditions and how to improve it.
My name is Danish Adrian Ben Azri. matrix number 103778, and I'll be continuing the next slide, which is experimental setup and scenario definition. The reason we're doing the experimental setup is because we want to evaluate the performance of stop and wait, go, back, and selective repeat ARQ protocol under different network conditions by varying key parameters. The tested parameters are packet loss probability, ACK loss probability, bandwidth, latencies, timeout interval, and window size. The next slide is scenario 1, which is ideal network. Scenario 1 represents an ideal or near perfect network environment. We kept the packet loss very low at 1% with no ACK loss. The bandwidth is set high at 100 Mbps and latency is minimal at 10 milliseconds. The timeout interval is reasonably low at 50 milliseconds, and the window size is 4 for go back end and selective repeat. This setup helped us observe the best case performance of all three ARQ protocols. It serves as a baseline that we can compare against more challenging scenarios later. This is configure network condition from scenario 1. The next slide is scenario 2, congested network. In scenario 2, we simulated a congested and unreliable network. We increased the packet loss to 20% and introduced ACK loss at 10%. Bandwidth is reduced to only 10 Mbps and latency is increased to 50 milliseconds. We also set a longer timeout interval of 100 milliseconds. These conditions are intended to test how each ARQ protocol handles frequent losses and delays, and how well they recover using retransmission. This scenario will likely show increased retransmission count and reduced throughput, especially for protocols that don't handle loss efficiently. These are configured network conditions for scenario 2. Next slide is scenario 3, high latency with varying timeout. The scenario 3 is designed to test protocol behavior under high latency conditions. Here, we simulate a long distance or satellite network by setting the latency to 200 milliseconds. Packet and ACK loss are low, and the bandwidth is moderate at 50 Mbps. We run the simulation with two different timeout intervals, 100 milliseconds and 300 milliseconds to see how critical timeout configuration is in high latency environments. If the timeout is too short, unnecessary retransmission may occur. If it's too long, the protocol may be slow to respond. This helps us understand how timing affects efficiency. These are configured network conditions for scenario 3. The last scenario is scenario 4, varying window size. In the final scenario, we focus specifically on window size parameter, which is applies to go back-end and selective repeat protocols. We keep the network conditions moderate, packet loss at 5%, latency at 30 milliseconds, and bandwidth at 50 Mbps. Then, we vary the window size, testing values of 2, 4, and 8 to see how it impacts throughput, bandwidth utilization, and retransmissions. This scenario helps us evaluate the scalability and efficiency of sliding windows protocol. Larger windows should generally improve performance, but may also increase the risk of congestion if too many packets are in flight during loss. These are configured network conditions for scenario 4.
My name is Mukri bin Zainal Abidin Saad. My matrix number is 105309, and I'm going to explain the data and charts. For the throughput is slowest in congested and high latency networks for the stop and wait protocol, indicating that this protocol perform poorly under adverse conditions due to its fundamental design. In contrast, selective repeat and go back end protocols exhibit better scalability and efficiency with larger window sizes in more favorable network condition. For the transmission time in an ideal network, the transmission is most efficient while high latency and congestion lead to increased transmission times. The stop and wait protocol shows the highest latency, illustrating the inefficiency in congested network. Selective repeat performs better than go back N in high latency, especially with larger window sizes. This indicates the critical role of window size in enhancing throughput and reducing delays in different network conditions. For bandwidth utilization, the selective repeat is the most efficient protocol in terms of bandwidth utilization across all network conditions, particularly particularly in congested and high latency environment. While go back N perform well with larger window sizes, but is still outperformed by selective repeat. Lastly, for stop and wait is not recommended for scenarios requiring high bandwidth utilization as it is consistently shows the lowest performance. For processing overhead, the stop and wait shows the highest processing overhead at 48% in a congested network, which indicates that it requires more resources to manage the waiting time. For selective repeat, it has a moderate processing overhead, indicating a balance between performance and resource usage. While for go back N, it exhibits the lowest processing overhead, suggesting it is more efficient in terms of resource usage, especially in high latency and ideal network condition. As for the conclusion, go back N has the lowest processing overhead, making it a more efficient choice in scenarios where resource usage is a concern despite its poorer performance in congested network. For retransmission, stop and wait, it requires the fewest retransmission, indicating its efficiency in handling packet loss, especially in ideal condition. For selective repeat, shows a moderate number of retransmission, suggesting it balanced performance and reliability. For go back N, it requires the highest number of retransmission, particularly in congested and high latency scenarios, indicating that it is less efficient in recovering from packet loss. So the go back N has the highest number of retransmission, indicating inefficiency in recovering from packet loss, especially under adverse network condition. Selective repeat performs better than go back N, but still requires more retransmission than stop and wait. For ideal network analysis and discussion, ideal network selective repeat perform best with the highest amount of throughput with the value 85 megabits per second, while go back N performed well with 70 Mbps per second but had more transmission, while stop and wait was inefficient due to single packet transmission limit. For congested network ARQ control analysis and discussion, congested network have high packet and ACK loss affected all protocols, while selective repeat handled retransmission more efficiently than go back N. And lastly, stop and wait had very poor throughput and very high overhead. For high latency control analysis and discussion, the stop and wait protocol suffered due to high idle wait time. Go back and utilize windowing to maintain performance, while selective repeat was most effective under latency due to pipelining and selective X. For window size variation control analysis and discussion, both go back and selective repeat improve as window size increase. Selective repeat scale better and achieve up to 90 megabits per second at window 8. Go back reach TMF1254 but had higher overhead than selective repeat. And lastly, for my part, the summary for best protocol and scenario. For scenario ideal network, the best protocol is selective repeat because it has the highest throughput and lowest overhead. While for congested network, the best protocol for congested network is also selective repeat because it is efficient. It has efficient retransmission under loss. For high latency, best protocol is also selective repeat because it has better pipeline efficiency under delay. And lastly, for window size variation, also selective repeat because it scales best with larger windows.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq Zikri, metric number 105225, and I will present our network design for Darmis Sdn Bhd. So, our goal is to create a practical, cost-effective solution that supports general internet usage, employee connectivity, shared printers, and secure guest Wi-Fi while meeting the project's requirements. So now let's look at the proposed network topology for Darmis Sdn Bhd. We have designed a star topology with a central enterprise-grade router as the core of the network. Both Office A and Office B are connected to this router via wired links, ensuring reliability and cost-effectiveness. Within this office, a dedicated switch connects all stationary devices such as PCs and printers, while wireless access points provide connectivity for mobile devices. Additionally, each office has a separate wireless access point, specifically for guest Wi-Fi, ensuring guests are ensuring guests are isolated from internal resources. So, for this diagram, it illustrates the physical and logical layout of the network. The central router sits at the core, connecting to both Office A and Office B through high-speed Cat6 Ethernet cables. Each office contains its own switch, which links to stationary PCs and printers. Wireless access points are strategically placed for employee and guest Wi-Fi coverage, while VLANs configured to keep employee and guest traffic separate. This design ensures efficient resource sharing, strong security, and scalable performance for future growth. Next is for the key hardware components. For routing, we recommend an enterprise-grade router such as the Cisco RV340. This device connects the local network to the internet and manages data routing between offices and external networks. For Office A, a 24-port gigabit Ethernet switch like the TP-Link TL SG1024D is used, while Office B uses a 16-port switch such as the TP-Link TL SG1016D. These switches connect all stationary PCs and network printers, providing reliable and high-speed wired connectivity. Next, each office is equipped with two wireless access points, one dual band 802.11 AC access point for employees, for example the Unify APS-C Pro, and a separate 802.11 AC access point for guest Wi-Fi, which includes a captive portal for added security. For inter-office connectivity, we use Cat6 Ethernet cabling, which support gigabit speeds and provide a direct wired connection between the router and the switch on both floors. This setup ensures stable, high-bandwidth communication between offices and shared resources. Next, for wired connection, we choose Cat6 Ethernet. Ethernet because it is cables that are practical and cost-effective. It also supports up to 1 Gbps, more than enough for the 500 Mbps internet connection. They ensure low latency and high reliability for all wired devices and are easy to install within the same building. Next, the single enterprise-grade router not only centralizes network management but also supports advanced features like VLANs and quality of service. It also helps us allocate bandwidth efficiently and securely. For wireless connectivity, 802.11 AC access points deliver high-speed Wi-Fi for mobile employees and guests. Employee Wi-Fi is separated from guest Wi-Fi using VLANs. which enhance security by preventing guests from accessing internal resources. This segmentation also allows us to prioritize bandwidth for employees and simplify network management. Dual band access points are affordable and provide the necessary performance for a small office environment. So, in summary, our proposed network solution uses a combination of wired and wireless technologies to balance performance, security, and cost. A center router, high-speed cabling, managed switches, and dual-band wireless access points ensure that all users, mobile and guests, have reliability and secure access to network resources. VLAN segmentation keep the network organized and secure, while scalable components allow for future growth.